Welcome to this explainer. Today, we're diving straight into the hidden, highly engineered world of fluid dynamics. I'm talking about the massive network of mechanics operating completely out of sight, behind the walls, beneath the floors, and under the streets of our modern infrastructure. We usually just turn a tap, adjust a thermostat, or grab a glass of clean water without giving it a second thought. But behind literally every drop of water, every circulated chemical, and every transferred fuel line, there's a specific, meticulously designed machine working around the clock. So today, we're popping the hood to understand exactly how these hidden mechanics actually pull it off.
Just take a look at the sheer variety here. What you're seeing is an overview of 12 totally distinct pumps that power the modern world. It ranges from your standard centrifugal pump up at the top, all the way down to highly specialized peristaltic and jet pumps. The scale of the engineering here is absolutely incredible. But hey, don't let this massive list overwhelm you. Our goal today isn't to just blindly memorize 12 names. Instead, we're going to group these mechanical marvels by their specific actions to demystify exactly how they manipulate physics to get the job done.
So here's our roadmap for today. First up, the power of impellers. Second, submerged and specialized lifting. Third, reciprocating and flexing actions. Fourth, gears, screws, and rotors. And finally, matching pumps to applications. All right, kicking things off with Section 1, the power of impellers. It is all about high-speed rotation. So the foundational concept we need to lock down here is the impeller itself. Simply put, it's a rotating mechanism used to increase the velocity of a fluid and convert that speed right into pressure energy. Picture a spinning wheel with curved blades housed inside a casing. As fluid hits the center, those spinning blades violently fling the fluid outward at massive speeds, creating the pressure that ultimately shoves it through the pipe. It's a remarkably simple but incredibly effective action, and it's the core mechanic for our first major category of pumps, which you'll find in everything from giant HVAC systems to your town's basic water supply network.
And this is a brilliant example of how engineers take that core idea and scale it up. Over on the left, we've got the standard centrifugal pump. It uses just a single rotating impeller. It's a reliable workhorse, fantastic for standard water supply, irrigation, and basic chemical transfer. But take a look at the beast on the right, the multi-stage centrifugal pump. This one features 2 or more impellers stacked in a series. So why do this? Well, by passing the fluid from one spinning impeller directly into the next, you exponentially ramp up the pressure. That's exactly why this multi-stage setup is the absolute backbone for high-pressure situations, like reverse osmosis water purification and the intense environments of the oil and gas industry.
Building right on that impeller concept, we have the vertical inline pump. Now, this uses the exact same centrifugal spinning action we just talked about, but it fundamentally flips the physical layout. Notice the vertical configuration and how the suction and discharge are in line. By standing the pump straight up so it sits directly in line with the piping, it saves an absolute ton of floor space. Anyone who has ever worked in a cramped mechanical room knows what a game changer that is. Because of this clever design shift, it's perfectly tailored for pressure boosting and large-scale cooling water systems where space and efficiency are at a massive premium. Moving right along to Section 2, submerged and specialized lifting.
Now, unlike the pumps we've looked at so far, which sit high and dry outside the fluid and pull it in, a fundamental design requirement of the submersible pump is that it operates completely underwater, or under whatever fluid you're pumping. It's totally hermetically sealed. By pushing the fluid from the inside out rather than trying to suck it up, it completely sidesteps a nasty physics problem called pump cavitation. Because of that, being submerged makes it the absolute perfect mechanical solution for handling raw sewage, dewatering flooded construction sites, and deep drainage tasks.
Then we have another specialized lifter, the jet pump. And the mechanics here are super fascinating to break down. Instead of relying purely on an impeller, it uses a neat 3-step trick. Step 1, it utilizes a highly pressurized jet or nozzle. Step 2, as the fluid blasts through that nozzle, it creates a vacuum that actually entrains or pulls in the surrounding fluid. Step 3, all of that combined fluid is efficiently lifted up. Because of this clever entraining action, the jet pump is incredibly effective at generating high suction lift. That makes it the absolute go-to choice for pulling well water from deep underground or for low-flow sump pumping. All right, Section 3, reciprocating and flexing actions. We're shifting gears from spinning to pushing, squeezing, and flexing. Both of the mechanisms here fall under the broader category of reciprocating motion. That just means a back-and-forth action. On the left, the classic reciprocating pump uses a solid, rigid piston or plunger to forcefully shove fluid out of the way. Think of it basically like a giant, highly mechanized syringe. That makes it perfect for extreme, high-pressure dosing and chemical injection. But look at the diaphragm pump on the right. It takes that exact same back and forth motion, but applies it to a flexible diaphragm. Because the diaphragm flexes rather than scraping against the walls like a piston does, it doesn't get jammed up by gritty or thick materials. That specific mechanical tweak is exactly why the diaphragm pump is the industry standard for moving heavy, messy stuff like sludge, highly viscous fluids, and even paints and inks.
Now, the peristaltic pump has what is arguably one of the coolest actions on our list. Step 1. Rotating rollers physically pinch and compress a flexible tube. Step 2. As those rollers travel along, that compression literally squeezes the fluid forward through the tube. The beauty here is that the fluid never actually touches any part of the pump mechanism, only the inside of the sterilized tube. Combine that with the fact that the rollers provide exact measurable squeezes, and you achieve Step 3, incredibly precise dosing. This highly controlled squeezing action is exactly why it's heavily relied upon for laboratory use and super-sensitive pharmaceutical transfers.
Section 4. Gears, screws, and rotors. This is where we get into the heavy-duty viscous fluids and sludge. Let's group these three heavy-duty workhorses together. If you're dealing with really thick viscous fluids or nasty sludge, these are the mechanics you absolutely need. First, the screw pump. It uses a massive helical screw rotor to gently, but very forcefully, push fluid axially down a chamber. Perfect for heavy wastewater or moving huge batches in the food industry. Next up is the lobe pump, which uses two or more distinct lobes spinning in opposite directions to push fluid forward. You'll see this one heavily favored in hygienic food and beverage applications. And finally, the gear pump. This one literally uses physical meshing gears to trap fluid between the gear teeth and the outer casing, pulling it directly from suction to discharge. It's incredibly tight and precise, making it ideal for moving dense liquids like hydraulic oil and transferring fuel.
Taking a slightly different rotor approach, we have the vane pump. So instead of meshing gears or big clunky lobes, this guy uses a rotor fitted with small sliding vanes. As the rotor spins, centrifugal force pushes those vanes outward, trapping the fluid firmly against the pump wall. Now, in stark contrast to the heavy-duty sludge pumps we just looked at, this sliding vane mechanism is actually ideal for very low viscosity fluids. We're talking thin, slippery liquids. That's why you'll see vane pumps heavily utilized in delicate lubrication systems, specific hydraulic setups, and complex vacuum applications.
And finally, Section 5, matching pumps to applications. Let's tie this all to the real world.
When you stack three drastically different pumps side by side like this, the core lesson of this entire explainer really clicks into place. The specific mechanical design 100% dictates its real-world utility. I mean, you wouldn't use a highly sensitive, precise peristaltic tube roller to try and move raw sewage, right? For that, you absolutely need the totally sealed, submerged operation of a submersible pump. And you wouldn't use that submersible pump to carefully transfer heavy, lubricating hydraulic oil. You need the tight, fluid-trapping mechanical force of the meshing gear pump to handle that. The engineering here is so intentional. Every single pump on this list exists as a direct mechanical answer to a very specific physical problem. And that brings us to the end of our deep dive into these incredible fluid-moving machines. But before we wrap up, I want to leave you with this question to ponder today. Which of these 12 mechanical marvels is quietly moving fluid behind the ones of your home or under the floors of your office right this very second? The next time you turn on a faucet, bump up your AC, or drive past a massive industrial plant, I hope you have a newfound appreciation for the incredibly varied, brilliantly designed hidden mechanics that are constantly working to keep our daily lives flowing smoothly. Thank you so much for joining me on this explainer, and keep exploring the world around you.